Yeah, that's the idea for the 45 minutes. Right? You don't have to go anywhere. So I'm glad I'm here. I was just incredibly sick yesterday. You know, the classic 24-hour, just horribly sick. But they'll teach me to go to what's that?
Was it from your little people?
No, I really don't know. But it was just the emblematic 24 hours. You know. So anyway, so I'm alive. Yeah, pretty bad. But I'm a little bit delirious still. So we'll see how we go. Okay. Getting better as the day goes on. All right. I started this thing, for example, right? Yeah? 5, 4, 3, 2, 1. It started? Okay. We good. Okay, so we talked about contagion a little bit. Just a few little intro things. We talked about contagion, right, in Principles of Complex Systems. We'll go into some more detailed math versions of that stuff in... which ones work? Is that good? You feel sleepy? Too sleepy? I don't know. Yeah, so we talked about, in particular, we kind of attacked this R naught thing, right, for being just ridiculous, which is this average number of people that one person typically would infect. And it's a nice idea. It comes from a 1920s differential equations model. Right? It's the simplest thing you can imagine. But it's been taken to the extreme, and it's still hanging around, 2010, right? We're still using this thing. So you want to measure, so there's an outbreak, so SARS is an outbreak of SARS or swine flu. We love this idea that we could then just turn that whole complicated event into one number. And then we can compare them, right? So we can say this is a really infectious one, and this, okay. So, that was this big thing we criticized. The other, and buried in that is there's no movement, right? And so that's what's, this is complex networks. That's been the big transition. We saw this paper the other day from the two Dirks, Brockman and Helbing, about people's disease spreading around the world. Just a model, but spreading around the world through airline networks. Okay, so there was a paper that appeared on the archive. Just to show you, you have to know what you're doing. A couple of when did it appear? 17th of January. So they just use the SIR model. So the problem with this is that it's random mixing. It assumes random mixing, which is not a very good model when you get to the world, right? Or you have to think about networks at that point. You have to think about how people move around. So we know that we've got all these kitchen sink type models that start to kind of address that. But as I said, it took a long time for even say the CDC to kind of move beyond these kinds of models. All right, so that's what they're using. And maybe some of you saw this, but what they started to attack, do they have a figure in here? All right, okay. They're doing fits. This is Facebook, and I think it's from Google Trends. Is it from Google Trends? Yeah, Google search query data, right? So searching for Facebook. And the comparison they want to make is to his MySpace, right? So MySpace is kind of, bought it. But then the fit is, and so they get an estimate here of, how long Facebook is going to last, right? So they're predicting the demise of Facebook well before 2020. Using an SIR model. Okay, so very first thing is that, that Facebook users are randomly mixing around the world, right? So that's probably not right. Okay, so Lara Adamic and a couple of others, and I've never actually met her, but we've contacted each other over the years, and she's done all sorts of great things. And she's a Michigan information, what do they call it? Information Department Center, something. So they have this very kind of amusing piece, right? Recent work by Princeton researchers. So here's searches for these are likes actually for Princeton on Facebook, and this is Harvard, this is Yale, this is for their pages, right? This is Google Scholar. This is mentions of Princeton in Google Scholar. So here's 2020 here. So here's the predicted end of Princeton, right? This is a correlation between this is Google Trends. Yeah, they should have basically looked at Princeton. Google Trends and its undergraduate enrollment, and the suggestion is that it will disappear by 2020. So anyway, it's fun to read because they're being, quite smart and so on. Anyway, we try to do good things. This is what, one of the It's what should happen in every class you go to, but it's a big deal for us. There's lots of madness out there. Anyway, just in this SIR model, this must, people have it, they talk about it, this must apply to everything. They refer to this paper by Goffman in the 60s, which is worth looking at. I mentioned it in POX, which just says, okay, we can use this SIR model for ideas and religion, and let's just do it, right? Okay, so social contagion, different thing. All right, okay. Oh, my daughter made a Roboctopus. Roboctopus is the mascot of the Complex Systems Center, and she built this one in Minecraft. This is pretty big, actually. Each little block in there, it took a long time. So that's pretty cool, yeah. So we could have a whole Minecraft thing. For a while, Second Life was this thing that you might build this place, Maybe it's Minecraft. All right. Okay, people. All right. So the delirium continues. Okay, we went through, I just started off, I mentioned supply networks and so on and branching networks. In general, we had this little video. I've actually shortened that up a little bit, so if you want to look at that again, it's a bit easier to look at. But okay, so we're going to go. Again, you can help me because I don't know what I'm doing. Wow. Okay, so I'm going to show you in this set of slides. So there are two pieces. There's branching networks 1 and 2, right? There are two sets of slides here. I've fixed them up a little bit, so I need to upload them again too. If you're looking at them, they might be a little unhealthy. The first set, I'm just going to give you a bunch of definitions and observations about real networks, and then we'll see how they're connected to each other, right? These in the second set. Yeah. Now, ultimately, you want a mechanistic explanation for why these kinds of networks appear, and they have particular scaling behaviors and so on, why they might appear. This is incredibly, there's a basic science aspect to that, and then there's things like Mars, right? So if all sorts of applications. One that has been a bit exciting at times was, it's over now, we know about the water thing, but what's been going on in the past there? So if you see some network structure, is it from avalanching, or is it clearly from erosion? Did water exist? So that's a hard problem, right? And they're related to that is, so if you've got some structures, say stromatolites, everyone heard of stromatolites? Are these kind of funny things that have grown in some way, and they're rock and so on, right? They're funny things. But a question with those is, could it be biological in origin, or could it also be just geophysical, right? So if you go to Mars and you find some structures like this, is that evidence of life in the past? All right, so there is that as well. So there's the basic science. How do these things come about? And then there are all sorts of different kinds of applications. Okay, so we're going to talk about river networks, but you can think, and we will touch, of course, on, as I've said, another very prominent kind of branching network, which is sitting inside you, right? Arterial and venal blood networks. But we'll use the language of river networks. So a drainage basin is going to be, so we pick a point P on a landscape, right? So just pick a point P, and then you find the area that drains into it, right? So that's going to be the drainage basin. So you can talk about points on hill slopes as well, but it really makes sense if you're on the stream. So basins contain basins, right? So there's this whole basin here, there's a basin inside it, there are basins, and as you march up, you can go to any point here, and there's a basin, right? Basins inside basins. Okay, so we have to contend with that. Yeah, it's and there's some really nice math and all sorts of stuff connected to this, but okay, all right. Okay, delirious. All right, so in principle, it's every point on a landscape. So if you imagine, these are if you go out into the field and these are the ones you see, you can see there's actually a drainage basin in here, right? So you can actually see there's a channel, right? So there's some point where you go up to the top of a channel, a river, and this is the end of it, right? You've come to the top of the Nile, right? But there's actually some limit. Here you'll see these, and we saw this in the Manyasco shore thing, right? You'll see these rounded hill slopes. Now for us, inside us, this is, our cells and so on in between the blood networks, right? The stuff that helps us run around or whatever it is, or think. Not very well. Okay, so, but on these rounded hill slopes, you could kind of imagine, you pick a point, and in some sense, the drainage basin is just really kind of like a line, right? You imagine dropping water on this this nice smoothed out thing. There's no actual channels on it, but in some sense it's overland flow, and some of it seeps in, but okay. All right. So they're linear. So this is this statement, right? So that on these what are called hill slopes, you see these little linear pieces, and then they start, right? So there's all this drainage into here, and then it becomes a channel. So if you have, you'll have flow underneath, tricky things to deal with, flow on top. You will treat that as following the gradient, right? Just simply following the gradient of the surface. I could add some more good stuff there. It's for large scale networks, that's fine, right? Actually, for really large scale ones, and that's what we'll think about, the US, Africa, right, Europe, the big scales. It's basically flat, right? If you look at from a distance, right? If you laid it all out, thousands and thousands of miles across, and then not so high, yeah. So it's basically flat. All right. So here are a few more definitions, right? So this is a little. It's a different picture. Okay, this is an example, right? So the basins within basin story. So we're going to have a couple of things we'll define. So there's L parallel. So this will be the longitudinal length. These are just good, normal kind of length things. And this is L perpendicular. So this is the width and the length of the whole thing. We'll just call this L and generally mean this. So this is a bit of a hard thing to define in some ways, right? So how do you orient this L? But there's an outlet to this whole basin, and so you can imagine doing various things. You could maybe divide this in half or something like that, or follow the typical kind of linear slope there. But basically, we have some idea. There are various ways we could, bring that about. But they should all behave in the same way. So there's an overall area. That's what this A is for this big basin here. And then there's a thing called the mainstream length. And so this is a little bit of a humans, walking around on actual landscapes, measuring things. Kind of makes sense in that. But, we care about the rivers, right? So you find the longest stream in the whole thing. So you have to start here. There are other, again, principal ways of doing it. You'd find maybe every junction you come to, every fork, you'd go up the most dominant one at that point, right? So keep following that up, and eventually you get to some end. So we'll call that the mainstream length, that L. Okay, so we have A, we have this is what I want it to be, this curly L / ELL, good. So that's the longest one. This can be fractal, right? So this can be a little curvy. That's where the fractalness will come in. Area is area, there's nothing funny about that. Although the boundaries of these things tend to be fractal as well. Fair enough. Yeah? Okay. All right. I guess that's fair enough. Little fruity in the head. All right, so that's just the basic story, okay? And there's going to be a bunch of other things we're going to define, but that's the basic plan. And then we have, right? So if we go to this point, then we have another little basin in here, and we'll call them A prime and L prime. They have their own little picture. The idea is, well, what's the shapes of these things? If this guy was scaled up and put over here, would it look somewhat like it? How do these things? Is there a recursive structure that's really clean? And of course there will be. All right, so isometry, you guys have seen. We didn't really. Last POCs we did a little bit. The ones before that, everyone else you saw a lot. But we certainly, we got into scaling. But right, so isometry just means that you scale up. If it's in 2 dimensions, you scale up uniformly in both directions. 3 dimensions, its scaling is the same in all dimension. Allometry means that when we so other, right? ISO is same, allo is other. The scaling, if we have a series of trees of different sizes and we want to rescale them to see if they look like each other, then we have to scale 1 dimension faster than the other, right? Maybe 2 have to be scaled faster than the third one, etc. So trees don't really follow this funny little sketch, but we looked at nails, for example. That was one example. It has some nice stories to it. All right, so the idea is that basins are allometric, and river basins are, and same with the blood network story. but we'll get to this. So L, and again, we have touched on this in POX for sure, but this is going to be a much richer story. So L is proportional to area to the h. So this is called Hack's exponent. Get to that. That the mainstream length is proportional to the overall length to the power of d. So this is the fractal bit in here. If this is greater than, so it's got to be greater than or equal to 1, right? So if this is this little length of this guy, the little l, is longer and growing longer than the overall basin length, then this d will be a little bit greater than 1 potentially. Depends on where you are in the world. You can put those guys together, right? So if these two are proportional, so a to the h is proportional to l to the d, then we have a is proportional to l to the d divided by h, right? You could just, okay, so you take this guy and raise it to the power of 1 over h, and you get this. So that's how the area is scaling as a function of overall length. So if this was all isometric, this would be L squared. Fair enough. This would be 1, and this would be L is proportional to 8 to the half. Okay. All right, so Haxel, so this is from 1957. It's a very well-cited paper. It was an interesting observation. Came up with 0.57 for a particular, some badlands in New Jersey, I think, somewhere. Is that possible? We should look it up. I don't think it's in the Dakotas. Anyway, but it was done by measurement, right? You're sitting out there with, scope things and stuff, and surveying, and horrible, and and in general, so Hack had 0.57, and then people sort of reported a range of different exponents. So this is a great mystery, right? If it was just 1/2, this would be completely boring. It would be dimensional scaling. It would make sense, right? This is meters, and this is meter squared, and it all makes sense. So it's been, and physicists got excited about it at some point, and they're like, "Oh, well, we will explain this, right?" Yeah, it's a dangerous kind of thing that happens. So and so this is a weak one, right? This is the mainstream length again, scaling as the overall Euclidean length. 1 point. Sometimes it's just flat, and then up to 1.1, right? So a very weak fractal nature in this thing. And if you put these guys together, basin allometry. So this is, people are finding that d is not all together, but d equals 2 again is isometric, less than 2. Means this: the basins are elongating. So as you go up through scales, the Euclidean length, the overall longitudinal length, is growing faster than the width, right? So they're getting longer and thinner. That's the implication, right? Allometric scaling, right? So that term was one of the Huxleys came up with that in the 30s, as we talked about. It's taken a while, really, even in the last 15 years, for people to start using it in lots of other places, usually in biology, but now we would say here and lots of other areas. Big fans of the allometric scaling. All right. So it turns out, so that's just a few, so there are all these other relationships floating around that people have discovered in different ways, or proposed, or come up with in different ways. And we're going to talk about, in this set of slides, we're going to talk about these, in particular, Tokunaga's law and Horton's law, and they have some really kind of great, great origins. What is that doing there? Okay, fix that up. So we'll get to what they are. So we don't know what they are. We've seen this as scaling of basin widths are sitting there. This is our old friend scale power law size distributions, right? So if you randomly select a position somewhere in the landscape, then the length that you measure, of the mainstream length from there, and the area of the basin that you find, right? They follow a probability distribution that tails away with a power law, right? The statistics of surprise. So most of the time you get nothing, right? If you're just poking around in the US, trying to find, and then sometimes you get the Mississippi. Very rarely. You get it at New Orleans, right? And you're like, oh, it's huge. But most of your sampling is like, no, there are no rivers here, right? This is, of course, idiotic random sampling of a large continent. And then there are some others floating around. People proposed all these. So this is a scaling of basin areas. We had that. This is Langbean's law. This is a sum of all of the stream lengths in the whole thing. various other kinds of things in here. Crazy things. So you can actually show that these are all related to each other, right? And this is a very natural kind of thing to do. They're all these scaling relations. Pretty much they're all scaling relations. Yep. They're ordered in a certain way because I'm going to say that these are sort of the most primitive ones. This work is from the 40s. This was published in 45. This starts in the 60s, and I remember seeing it being talked about by Don Turcotte, who's a famous geophysicist, in maybe 96 in Santa Fe, and he was saying how all this work had been done by this Japanese researcher and no one knew about it. Please know about it. And it's really cool. But it was inspired by Horton's law and showed all this extra detail in there. So we're going to show how these things are connected to each other. All right, and again, all those parameters for those laws, they have all these values that people have measured in different places, often for small scale ones and so on. But the game is, well, is there a universal kind of pattern? How much does it matter about geology? We're not going to solve that problem today, but or anytime soon. But it's you see the game. It's kind of like, well, what? Right? We love the universal stories. All right, so all sorts of things. So we have to pin all these guys down. But it would be good to not have to, come up for a rule for each one of these. But if we can see that, this guy depends on a bunch of the others, we can just discount a little bit and just say, okay. So they're scaling relations, and we'll get to those. All right, so we want to find out how these things are connected. What's the most essential description? Because this is getting towards explaining the whole thing, right? So we're going to pare it down to its essential description. And then when we make models or we simulate things there are only actually recently, I think in the last 15 years, experiments where people have been able to make decent landscapes, right? Because most efforts to do that, you put some dirt in people have these things, right? Right? As scientists, you fill a thing up with dirt and then you spray it with water, and you're trying to mimic a continental scale situation. So if there's some problems with that, the whole thing just washes away, right? So it's hard. You have to make up some sort of mess of different kinds of materials so that will erode in a reasonable way. That's why people go to computers, I guess. All right, this is the tricky part, right? What are the origins of where do these things come from? Lots of people have attempted to do this, but it's not been sorted out. And then partly this 3 got ahead of 1 and 2, actually, in the classic way of scientists. We'll explain everything. And it turned out that we hadn't quite figured out everything at the start. Okay, so here's the sequence to start with Horton. So there's Strahler as well. So Horton in the 40s came up with this so-called stream ordering, right? So, here's this big network. We need to somehow start giving things labels and kind of breaking it down and starting to look at the architecture, right? Tokunaga's is really about law is about architecture, but this is what this is doing. Architecture is an excellent word, beautiful word. So people will call it Horton stream ordering or Horton Strahler stream ordering because there's some nice tweaks made by Strahler in the 50s. So you can think of it as an iterative trimming of a network. So here's the well, we'll get to it in a second. We need to talk about a few things. So these are the channel heads, right? Okay, that's where the flow is focused enough that it actually starts to incise into the landscape. For us, it would be where our capillaries are, right? Which are pretty weird, right? It's sort of one blood cell can kind of get through those guys, right? We're pumping out blood. It's pretty fast at the start, depending on what you're doing, but it's it's fast and it's a big kind of flow. It's pulsatile, which is weird, right? Because you have, that's not true here, but the networks inside us, the tubes actually kind of squeeze, right? I mean, your heart is pushing stuff, but they actually go like this. The tubes are flexible, but it has to then, you get an extra bit of branching at the end. We'll come to this later on. It's called Murray's Law. You get a more rapid branching ratio. The branching ratio changes, and that slows everything down. So it's basically like, going on a bus, right? So you take off and you're a blood cell and you're like, yes. And then like you're going down this some kind of surface and then with a helmet on. And then towards the end, it flattens out and everyone just slows down a little bit, right? And then the blood cells a little bit of diffusion goes on and then they like ramp it back up and get back up to the ticking unit in the middle. All right. So, okay, channel head. All right, so that's the channel head. So we'll call a source stream that these little dashed ones here, right? So they start from a channel head until they run into a bigger thing. So that's a source stream. As I said, kind of like capillaries. And then we'll order them 1, 2, 3. So this is an omega or an omega. What do I say? Omega. I say all these things in stream. Omega. Does that hurt?
Yeah, it's awful.
It's pretty bad. Okay.
So it's
Capillary is good. Which one is it? The
capillary.
capillary. Capillary.
Like corollary.
Yeah.
You say data?
Do I say what?
You say data or data?
Oh, I say data.
I do too, and I get.
Where do you get? But,
I think I got it from you.
oh yeah, it's my fault. I apologize. I know. There's a lot of English speakers, like English, who seem to have accepted the big data part. Well, they're going on like this and so on, and then they'll say big, data. I'm very tempted at times to give a whole lecture in like a Severus Snape accent, but I haven't quite reached up there. Because I do all these accents for my kids when I'm reading books to them. Okay. Very good Gollum in my pocket, I have to say. Which has been outlawed at home due to its nastiness. Okay. Just doing a voice. All right. So, all right, I'll persist with my ridiculous way of speaking. Data. Good. Okay. Yeah, that's what someone with the stroking a white cat on a swivel chair, kind of the evil overlord would definitely say data. So, all right, so we're going to label all these source streams, all these dashed ones, and we're going to call them omega equals 1, and we'll then trim them off. Think of it like this. So they've been removed, and then we have a new set of source streams, right? So we sort of just do this recursively, and we'll call those omega equals 2, beta. Sorry. Schedule. That's really bad. Yes. There's a start to 30 rock on one of them where Tufa says 3 like charades and schedule, and he says one other word, and I'm like, they're all. He gets excommunicated for. But all of those pronunciations were fine. Like, what's wrong? Okay, so schedule is pretty bad. So let's see. So they're all source streams. They're all omega equals 2, and we're going to get rid of those guys, and now we have this guy. Okay. So you imagine for the Mississippi, it depends on the resolution, right? So the work I'll show you is when we had resolution of say a mile or 1 kilometer from satellite data. And so you have your big model of the whatever it is, the continent, and then you drop little bits of rain, pretend rain, and let them fall down the steepest descent. And that traces out a network. But if you had someplace you have 30-meter resolution and even more, right, in terms of the structure. And I guess maybe I could come back to this. I wrote all these very elaborate kind of code for. So what happens is if you run, which makes sense, right? So you'll run into little lakes. I mean, there are actually literally lakes, of course, but you'll also run into, and they're just flat on these models. You'll also run into places where you get stuck, right? So your little bit of water is coming down, and it gets stuck in a little hole. So you have to kind of backfill them, and then let it run off the edge. But if you have more resolution, you'll have more of these little things get stuck in. So there's a whole process where you kind of fill in lakes and so on, and then let streams go. All right, okay, I think we've got the idea. And the last one we'll call big omega. And then we'll say the whole thing is of order omega. So this is an order omega equals 3. This is order 3. This basin is of order 3. That's an order 1 stream, that's an order 2 stream, that's an order 3 stream, and the whole thing is an order 3. Okay, cool. So you can do the same with blood networks. And people have done that. You can read papers about how they did that to little organisms by somehow removing the organism. Okay, so we got the plan. Okay, so this gives us a schema for the whole thing, and we can start to say, well, what are these little order 1s like, and the order 2s like, and the order 3s like, and then how do they fit together? So there's a hierarchical structure here, but it's not a simple hierarchy, right? So there are order 1s going into order 3s. So you have to start thinking about that. When we say order 1, 2, 3, 4, you start to think, well, it's a pure hierarchy, right? I mean, your brain can easily go in that direction. But actually, these order 1s are going to be going to 2s and 3s and 4s and 5s and 6s. So there's it's a mixed kind of hierarchical structure. Look at this color scheme. It's terrible. I'm actually going to redo that at some point. This is what happens when you just use the raw. I was trying to find the original figure. Pretty nasty. Yeah, you should not do that. Yeah, little green screen, blue screen. Just, yeah. Yeah, the default setup in a lot of these things is bad. Okay, but this is the Mississippi, and this is just the top. As I said, it's a mile resolution. So it's just the top 4 orders. Right? So this turned out to have be order 11. So you see there's a bit of an oddness to this. It's prone to, so if you rescale things, or you get more data, right? So say you go from, maybe you get a tenth, a less coarse grid, or you'll coarsen your grid the other way, which you can do because you have the data, but you could get it less coarse, say, there's an improvement. Like I said, goes to 30 by 30 meters, something like that. Then, this won't be an order 11 anymore, it'll be an order 13 or something. So there's a bit of a oddness there. But these are one of these scaling stories, the kind of the whole fractal thing. The internal sort of structure should work in a similar way. Okay, so there's some funny things to just observe about this. First of all, here's our order 11. There is an order, it's hard to see this, but there really is an order 10 structure here. I mean, 2 order 10s. And I have to get to something in a minute. But let's take the order 8s. You can imagine pulling those guys off, and then the ones that are left, these new source streams, right? Source streams are the red ones. What's missing is that there's a tiny little blue one in here. Actually, there's a tiny little blue one in here. We'll get to that in a little bit, because we have to define how they change. But they're of different lengths, right? So these guys are relatively long. There's some small ones, right? These are quite small. This is small, relatively. So there's a big variation in these things. So we have to kind of cope with that as well. Okay. All right. So another way to think about ordering, right? So we'll start again with all of these source streams. Again, it doesn't matter too much, but they're all right. But let's imagine these are all source streams. They're all order 1. So this is a simple thing to think about, I suppose. But all right. So imagine you follow them down. Whenever 2 order 1s hit each other, they make an order 2. So that should fit in with what we had before. But if an order 1 runs into an order 3 or 4 or 5, it doesn't change anything. Right? So this is the definition, right? So if they 2 streams of the same order meet, the resulting stream, so imagine this, has an order 1 greater. Right, so these 2 8s make a 9. As I said, those blues are a bit hard to see, but these 2 reds make this blue, so 2 9s make an order 10. But everything else is absorbed. You can imagine them all being absorbed. So we're starting to get into the architecture, right? So these order 9s are making an order 10. Everything that hits this as we go down just gets absorbed. It's still blue. Doesn't change its order. As I said, there's a tiny blue one here, and those 2 blues hitting each other make this order 10. 11. Yeah, sorry. This is okay. These are actually the same definition. Let's look. Yep.
If it gets lucky, it just has 4 red ones converge at the same time and vanish, like the black one. But if they all go line by line, you have a blue one and a couple red ones going one by one into it, and there's like 100 of them.
Yeah.
It'll still stay blue.
It will stay blue. That's right. Yeah. Yep. And actually, we'll see how that. We'll see typically how many come in from those sides, right? So that works. It's basically very similar to what we have inside us as well. So it turns out that this is yeah. I know it seems weird, but and the original Horton work didn't characterize this at all. Tokunaga is the one who sees what this architecture is like. It gets more and more elaborate, but. So if you have 2 streams that are of different orders hitting each other, then the resultant stream, as I've been saying, it just stays the same as the largest one. Okay, so it just gets absorbed. Right. So now we can talk about side branches. You can think of it as side branches, right? So these are the kind of the generative ones, and then these are all side branches. And there'll be so many side branches of order. Let's say we've got an order 7. There'll be so many side branches of order 6, order 5, order 4, order 3. But if the order 7 runs into another order 7, it becomes an 8. If it runs into anything above it, it just stops. And so you can encode, if you want to write down, Kronecker delta. So it's delta of, so it's the discrete version of the Dirac delta function. So you have two integers. This is equal to 1 if they're the same, 0 if they're not. It's a handy little character. Very nice little character. So it's the maximum of these plus 1 if they're the same. Right? So if they're the same, then this is just, they're equal to each other. The max is just the same again. And you get a plus 1. All right, you can think about what, yes? Yeah, so that's a good question. So sometimes that, I mean, rarely that happens. Usually there's a little bit of a gap. But physically, yes, a little bit. But we'll treat them as being separate. So in that case, you could, I mean, they could easily too also come in from the sides, perhaps, right? So we would just use the same rule, basically. Right? They just get absorbed in from the side. Wouldn't change it. But generally speaking, it doesn't happen. Usually they're forks. Cool. And you get very different things happening when you get out towards the sea, for example, right? So you start to get tidal structures and it's a bit of a different kind of networks up here, and there's all sorts of work on that as well. Okay. Talked about this. The resolution of the data is obviously a bit of an issue, but basically the micro description will change, but these kind of ordering relationships should be similar enough, right? So, and you can check that by giving the resolution you have, just coarse graining it and seeing what you get. But it's not super clean. Anyway, one can in principle imagine you have the whole thing perfectly lined up. So it's a way to discretize the network, and it helps us then start to describe network architecture, right? We have artificially discretized it, although, of course, there is this discrete nature. There is a stream, it hits another one, there is this kind of sense. So it does seem to be a reasonable piece. Okay. You could imagine having a much more elaborate one where instead of, there's been efforts to do this, right? So there would be different colors for all these pieces, right? This would have some encoding in here that it is a sort of an order 10 stream, but it's just the start of it, and then right, you could add more and more. There's some change in color here as you go down. So each stream segment, which we'll get to, has its own little kind of flavor. Overall, right? You could imagine something like that. So a more microscopic description. All right. Okay, so here are the things that kind of pop out that you can then start playing with. So you can simply count up the number of streams of orders, right? And so that increases as you go back up, right? So as you go down, you get less and less of them, right? There's one of the overall stream. So n of capital omega is 1, and then as we go back up, it grows. We'll have order omega basin will have this area A sub omega, and we can look at the average, and we can look at the distribution of these, right? So these are simply numbers; they're fixed. We can look at the area, as I said. We can look at the average. We can look at the distribution. We'll have a mainstream length as well. We can look at the distribution of that and the average. And these stream segments, as I said, so these are just the little pieces between each fork. Well, slightly different. So imagine here's your mainstream length, right? Or not mainstream. Here's your mainstream going back up here. Then it has 3 stream segments. It has this order 3 part, an order 2 part, and an order 1 part. So you can do that, right? So there's these are now segments. So you can think of this main stream as, it's order 3. It's made up of these 3 stream segments. So they should be connected, right? So this S omega is a sum of these guys, and that should be reasonable. Right. All right. So that's what this is saying, right? So the order 3 part is only this part of the stream, which is actually order omega. And so, for instance, here, and it will run until it, good, right? So it runs up until we get to order 2 basins, order 2 streams, and this one runs up until we get to order 1s and so on. Right, fine. Okay, so there are 4 big pieces, and we want to see how they're connected together. So Horton 45, and then a little bit later, we have Schum as well, found these relationships, that these are roughly true. So the number of streams of order omega divided by the number of streams of order omega plus 1. So again, that should be greater than 1, because we're decreasing. This is a larger number than this one. And the n just refers to this number. So this is roughly constant. So there is this self-similarity, right? It's popping out of this particular, we've defined things, we've described the architecture in a certain way, and then you go and look at the network and you get this. All right, so we have the same kind of thing. So the average stream length of order omega plus 1 divided by the average stream length of order omega. So again, these are getting longer on the other hand. So this is greater than 1. Right, so the omega plus 1 is swapped to over here. So they're defined so they're greater than 1. Right, so as you go down through the network, you get bigger and bigger streams, bigger areas, bigger lengths, but fewer of them. And then we have a similar one for basin areas. Okay? All right, so these 3 things are roughly constant. So that's a start. This is observed. And we're going to try and connect these pieces with each other and with other laws, and we're starting to build up this architecture. All right. So if you think about these, it describes, and this is an artifact of the way we've broken the network up. They describe exponential, that gives you an exponential growth or decay, right? So if you look at the number of streams of order omega, and we're going, get this right? Yeah. So that's you divide by Rn for the previous one, and then we keep going down and down, right? Eventually we'll get to N1. And I always like to think, so, how you go ... and you have to write down that last line. We know we're getting to N1, right? So we're decrementing through here, and every time we're adding 1 to this side. So this is always a bit tricky. You get to this and you're like, well, it's N1, but is this omega or omega plus 1 or omega minus 1? The way I like to think of it is you just add these guys. Omega minus 1 plus, maybe this is silly, omega minus 1 plus n, right? So that is constant. That thing's constant because you're decrementing that one, incrementing that one. So omega minus 2 plus n, this squared is what I'm talking about, this 1 here. So omega minus 2 plus 2, so I got that wrong. So this is omega minus 2 plus 2. So it's always omega minus 1 plus 1. It's always omega. So 1 plus omega minus 1 is omega. So you can always just sneakily fill in that piece at the end. You don't have to kind of think too much. All right. And if you write this down the right way, this is really an exponential. This number is greater than 1, so we can write that as a, right? It's Rn. We can write as exponential of ln of Rn, because we're sneaky. And it's on the bottom, so there's a minus omega minus 1 and all of this. So this is just some constant. It's because this is greater than 1, this is positive, so it's decaying exponentially. Just some sneakiness. Yeah. And so if we did the other ones, the stream length and area, we'd get a positive, it would be growing exponentially, right? So this way of describing the network gives us this is the way it's breaking up. It's breaking up pretty strongly, right? Okay, this exponential, they're quite different from each other. Okay. Odd. Okay, and so we get the same sort of thing for area and length. right? So instead of a minus here, they're growing exponentially. Right, so number is going down, error is going up, and length is going up, and exponentially so, right? Good. All right, so we have a sense of how these things are working. Yeah?
It's not e to the negative omega.
Yeah, so number does that. So there are lots of little streams, and only one of the major one, so it drops exponentially. But the major one is very big in area and very big in length, so it's growing. The little guy, yeah. So it's just part of the definition. It depends what people want to do, right? But we wanted to have all those ratios. The idea is all those ratios are greater than 1, which feels sort of okay. But there's a confusion. Yeah. Yeah. Okay. So these are laws of averages. Fair enough. It's across basins, right? Typically, if you do numbers, right, you're adding up numbers of things. You could do that, right? Yep. Stream lengths you have to, and areas you're looking within basins. You're taking all these basins within it. Of course, it's a bit funny, right? Because you have many little ones, so your averaging is really good there. You have one big one, so there's no averaging. So that's an interesting thing to do. So you can, if you find internal structure in this network, you can look at whether the largest stream or the overall thing is consistent. Is it actually consistent with the internal ones? We'll get to that, but basically you can kind of predict how long the Mississippi should be or the Nile should be based on its internal structure. And really what's happening then is you're getting to geological kind of constraints, right, that are shaping the overall thing. Just see if they kind of match up. So you get a lot of we've got a lot of this branching network structure out of this thing. Right, we've got a fair sense of this kind of hierarchical feel to it. But we need some more. There's also the stream segment piece that we talked about. So this is this guy, and then this. Yeah, it was mainstream lengths before. So this is this guy versus this guy versus this guy, as compared to taking this whole length here. So they have a scaling as well, and that's greater than 1. And so you can actually show that, for large enough networks that this has to be basically true, right? So the scaling of the mainstream length and the scaling of the stream segments is the same, right? So this is good. This is actually a thing for you guys to do. It's not too bad. But it helps you get a sense of it. All right. And it means that we had 4 numbers, these 4 ratios, we're down to 3. So we're going to keep doing that sort of thing. So that's helpful. We're down to 3. Compacted our story a little bit. These guys are actually better to work with because now we're really sort of more talking about the architecture of these things. Okay. Yeah. A couple of examples, actually in the real world. So this is the Mississippi, the Nile, and the Amazon. So we have stream order across here on the bottom, 1 through 11. And so you see, so all 4 of those Horton pieces are there. So number is going down in all of these, right? So there's only 1, 10 to the 0. There's only one of the largest order. So it's dropping here. And area goes up. And this is stream segment length and mainstream length. So you see they're scaling very similarly. So this is this is 1, 2, 3. This is just a normal linear scale. This is a log scale. One can appreciate there are many orders of magnitude here, so this is not bad. Yeah. It's heartwarmingly good. And you see, there's some variation just at the end and so on. That's all right. That's fine. Big scales. And you don't have as many out here to average with, right? These average scores out here. There's only one of these, so this is not a really good thing to average. So that's fine. That's cool. I guess stream segment length is only on one of them, right? What else do I want to say about it? So all right, you see those 2 match up. You might want to look at these guys, which is kind of interesting. Area and number. They're going in different ways, but they have some compatibility. Let's say that. All All right, blood networks. You can certainly see in sections of blood networks that people have messed around with. And we have all sorts of examples in the literature. You have cats and rats and so on, all the way up to humans, because someone was lying around on a table. It's a nasty business. I mentioned the other day. You can, various methods. One is just to get it all out on a slab, and the other is another one is to replace the blood by some sort of plastic material, and then remove the surrounding stuff, and then you actually have a 3D model, and you get in that account. Now you have another piece here, which we didn't really have in. It's not really talked about much, but there's a width of these channels, right? There's the width of the Mississippi as it exits. There's the width of its little channels. It's not really floating around in these other Horton laws, but you do certainly have vessel diameter, right? So you have the aorta size, the typical width of it, and capillary. So there's another one to think about there. And that really, so you have flow going through a tube. We have lots of good things. There's Poiseuille flow and pulsatile flow. These are different kinds of things we can do with that. We have analyses of those. Flow in an open channel, we have some reasonable stuff with that, but it's a bit more complicated. Okay, so this is some data from real blood networks. You don't have to worry about that first line. That's another stuff. Turcotte, I mentioned him before, talking about Tokunaga. So these are just some estimates of these things, right? So Rn is here. This is this little r here then is the radius of these tubes inside us, and then lengths of these guys. You don't have to worry about any of this, but you see some sort of consistency within organisms, and of course these are just two examples. These pieces here show you, this is the pulmonary arterial tree, I think it is. I mean, these are just different. It's not the whole blood network, right? Some piece of it. So that's complicated. But you see some consistency at least. Two randomly chosen humans who ended up being processed in this way had this structure. So there's some consistency, but it points to maybe there's just different. I mean, I think in the end with blood networks, it might be that having a branching network that obeys a general kind of set of rules produces a lot of good things for you, right? But it doesn't have to be a specific branching ratio. But it seems, some organisms might have their own typical ontogeny, right? For how do these things get produced, right? You have to think, blood network's growing, right? Angiogenesis is a very odd thing. Somehow you have to grow these networks going out, which then turn around and have to come back. And how do they keep growing with an organism? All right. Okay, so I've mentioned some of these before. So Horton's laws vary. This is reported in papers for very different kinds of networks. So there's no agreed kind of explanation. There are efforts to say that they're all the same, or that when you measured 3 to 5, you're all just getting an error around 4 or something like that. But no one's absolutely sure about that. There are toy models of networks that have very specific kinds of structures, right, that are universal within that kind of description. All right. Okay, so the piece we'll get to now is, so they tell us how we go from level to level. They don't tell us how these things are put together, right? That's really missing from this. And one sort of can get the feeling that they're purely hierarchical. So that's wrong, and which is wrong. And just as I showed you with this little example here, right? These side streams are coming in at all sorts of different orders. All right. Okay, so this is Tokunaga. So this is right where we'll get the architecture properly. And so there are papers from 68 and maybe, click on this thing, kind of interesting. Wow. It just disappeared. Yeah, so they're really spread apart. 66, 78, and 84. So I remember getting these papers, which are all in Japanese, right? With a little. Let's find one. This is fun. Okay, cool. So this was tricky. This is before, well before Google Translate and so on. Citations are there. What's that? Yeah, I did not read this. Did not read this. But it's funny, right? So there's a little bit of, so, you know, right? There's a Horton and so on. So there's a little bit, and I'm like, okay, it's kind of the right stuff. I don't know how I got to this, where I got it from. But lots of plots. And then there's a little, where is it? Let's see. Yeah. Yeah, so there's a little piece at the end in English, which helps a lot. I actually we'll get to this, but I derived this by myself separately and then found this, and I'm like, damn it. But, you know, that's also good. 'Cause you're like, I mean, it was 1966, yeah, right. But it took a long time for this to be, as I said, so it's 1966. It really took 30 plus years for this to become known. Okay, so there you go. So that's kind of fun, right? Tricky to work through. Math helps because some universal structure there. All right. So as you saw, Tokunaga is citing Horton and so on. So done a good job of actually going look at the literature that existed and use the same kind of stream ordering thing. But then he wanted to figure out how these things were connecting in from the side, right? It's also a law of averages, but a little bit better. All right, so there's this guy here, T mu nu. So it's the average number of side streams of order nu, right? So that's the second part, that are hitting a stream of order mu. All right, so in this little piece here, this is an order 2 stream. It has 1 stream of order 1. So this contributes to T21, right? Order 2 here, 1 on the side. This one has 1, 2, 3 coming in. Right. So there's also T31 and T32. You'd think about this, right? So here are the streams of order 3. These are guys coming in of order 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right. So these are streams that are being absorbed. You don't worry about the 2 generating streams. That's a separate thing. The generating streams are separate. Right, so you have 2 order 3s coming in and making order 4. Don't worry about that. So the stream that's absorbing it has to be at least one more than these side streams. Okay. Okay, so we have these 2 that are generating it. They're of order mu minus 1. They're not side streams. Okay, and eventually it gets terminated, right? It runs into, maybe there's a stream of order 4 here or 5 here or another 3, and that's the end of this one. So it's just you take anywhere between its start and its finish. Anything coming in there is a side stream. Okay. All right. So these are observations, and then we'll just observe from real data, and then sort of laid them out as laws. And the funny thing about this is they work for really arcane kind of models that aren't real kinds of networks. You can really make up anything that creates some sort of branching structure. Okay, so first of all, reasonable things. We've got a lot of there's fractal stories here, and as I said the other day, right, the Horton piece is really the first I think it is the first kind of quantified version of what would become fractals, right? I mean, people had talked in poems and said how these things are like each other in scale and something probably, but it was the first quantification. So this self-similarity would be reasonably encoded in for these Tokunaga ratios. We're going to call them Tokunaga ratios. So the T mu nu will be T mu minus nu. It has to be just the difference between them. So if this whole thing has a self-similarity, if this network has a whole self-similarity to it, right? So the number of order 7s coming into an order 10 should be similar to the number of order 1s coming into an order 4, right? So it's really just that, right? If you can really kind of resume and find similar structure, right? Order 6 is into 3, so the difference is 3. This should kind of have the same feel, right? Because we're doing that, imagine pairing things away, right? You get rid of the order 1s and order 2s and order 3s when we introduce stream ordering. If you do that, eventually, say you've got rid of the first 4 orders, your order 5 is now an order 1, and it should kind of look the same. Okay? Exciting. So there's that, and then, so that's just the first piece, but then, this is a much stronger quantification, right? So T mu nu in general, we'll start with a T1, right? So there's whatever the difference is between streams that are, this is the ratio for streams that are adjacent by 1, right? So order 7's coming into 8s, 10's coming to 11s, 3's coming into 4s. And then as you separate in order, you get more streams coming in, right? So there are more streams of, right? As you separate the orders between these two, it grows exponentially as well, just as we had for Horton's laws. Let's see. So when mu is equal to nu plus 1, right? Then this is 0, so we get T1, so that's our base. And then we increase by some ratio. Right. And usually we drop the whole T mu nu thing, and we realize that we've got just the difference between the orders that matters. And then this is the kind of structure. And typically you'll see this is about 2. It's on the order of 2, right? Exciting? Yeah? Okay. I don't want anyone to overdo it. All right, so this is a little side picture. This is about 2, right? The T1 is about 2 if you go through and look at these guys and you add them up. And ridiculously, this ratio is about 4. So I think I counted 9 of these order 1 guys in here. Like 1, 2, 3, 4, 5, 6, 7, 8, 9. And typically there are 2 here, so 2 times 4 is 8. So it's not bad. But it starts to look like a real network. This is Mississippi. So actually, seems to be bearing out. You have to think about how this guy works. So this is the average of this T mu nu guy. So again, it's equals approximately, of course, right? T1 T mu minus nu minus 1. So if we take the log of this thing, then it should grow with this difference, mu minus nu, right? That should be, okay, let's do it. So there's just an offset T1 plus mu minus nu plus 1 T. All right, good. So it will depend on this difference. This is some constant, this is some constant, and so this should grow linearly, and so on. So this is nu equals 1, so these are, for instance, this line here, so this is the number of first order streams that are coming into streams of order 2, and then 3, and then 4, and then 5, so it's increasing exponentially. And then as we move out to order 3, then we only have order, sorry, this is 2, so they have to start at order 3. So there are 2 ways to look at it. This is T1 across here. This is T2 across here. This is T3 across here, T4. Yeah. And then you can, yeah. Kind of okay. So it's roughly not, again, this is real data. It's messy. Things fall apart for the higher orders because it's just very poor averaging. But it's not bad. So, yeah, so this architecture seems to be, this seems to be the story, right? Okay. All right, so here's our nutshell for this, and then we'll try to connect these things. So lots of self-similarity, tons of scaling laws. I mean, there was just a whole bunch early on. Stream ordering is a good way of getting at this architecture. It's not the only way, but it's become quite accepted. You see the self-similarity there. It's not a pure hierarchy, and Tokunaga is really helps us get at this architecture. There's more underneath that as well, but that's the best place to start. So it's a mixed hierarchy, and then you can connect these things in nice ways, and then we can build up to these other things like these scale-free, sorry, not scale-free, these power law size distributions for area and length and so on. We can get to all of those guys as well. Okay, this is just ridiculous, but this is landscapes. That's what, let's make sure this works. Seems better. Yeah, Minecraft. So this is just to finish this set of slides. So these landscapes are pretty good. I mean, talk about creating artificial landscapes, right? So in Minecraft, you've got a spawn point, and then based on this world, everything's set up so that as you move away from that spawn point, more of the landscape unfolds, and if you come back to any point, it's the same thing, right? But it's always sort of opening and closing itself in a way. But this character here has, this was actually written up in the New Yorker, I think. This is, he's onto his 4th or 5th season of recording, going from his spawn point as to the edge of the Minecraft universe, which in principle doesn't end, but as you get further and further away, the idea is it's supposed to kind of actually get buggier and stranger. But he narrates this thing. You give money to kids. There's money that gets donated to kids if you follow this and so on with the ads. But it's pretty, it's pretty spectacular landscapes. What's that? So this is just generated. This is generated. Yeah, so there's building stuff, but this is generated. This is one of its things. It generates this landscape. So if you come back in, there will be this stuff again. There's some, rule. But we early on when people just going with fractals, we build these little fractal landscapes, and it was pretty exciting. But this is kind of impressive. So that's Woofy. It's apparently really a feature. So he tamed a wolf halfway through, and has become Woofy. Woofy was lost actually at some point, and he found him again. It was quite dramatic. But he's just a faithful little animal that runs around. But it's survival mode, so he could be taken out at some point. Naturally, there are zombies and various other things. Anyway, yeah, it's called the Farlands. This extreme limit of Minecraft is called the Farlands, which things go a little strange. But he's got a compass essentially, and he's just traveling in one direction. Night comes every 10 minutes, so he has to find a little hidey hole and bunker down in it because you can get taken out. Anyway.
So does it just keep generating terrain?
Yeah, and the claim is that it will fall apart a little bit towards the end. So making terrain look good. It's pretty amazing, really. I mean, you go back 30 years or 40 years and think about creating natural looking landscapes. No way, right? So anyway, that's super fun. There is your requisite video for the there was another one, but that was just yeah. Okay, so I'll just start this. Okay, so we're going to connect Horton and Tokunaga, which seems unlikely, but we can. We're going to reduce Horton a little more, get to some of these scaling relations, and then actually look, because these are all laws of averages, we're going to look at actually some of the details of these things. There are underlying distributions, quite spread out distributions, quite wide distributions for stream lengths and areas and so on. We can get to that. I'm going to talk about models briefly at the end. This has been sort of this quixotic kind of attempt to produce an explanation for the kinds of networks that we see. But as I said, there are some that work beautifully in that they make kind of nice looking things, but there's no one's sort of come up with it's sort of universal, but here are problems because of geology or something, or Africa is going to have a different thing to some other part, right? Because of we don't quite have that. I think we should. Okay, we'll start all this properly on Tuesday. Yeah, it's a good place to stop. What's that? Thursday. Wow. Wow.
I'm just making sure that we have.
No, I have no idea. Okay, so yeah, actually functional, sort of. So I said some words. That was an achievement. So there are office hours now. So happy to hang out and talk and put things here. Okay, all right. Thank you, people. So this will build. We'll go from branching networks, which have all this lovely rich structure. We'll get to these supply networks and redistribution networks, which have magnificence, right? Where do you put your Starbucks? Where do you put your hospitals? Where do you put McDonald's? You know.
All next to each other.
That's an extra piece. Yeah, that's very clever too, but that's an extra piece. Well, they're trying to maximize different things, right? So Starbucks is trying to maximize simply the number of people coming in the door. Hospitals are trying to maximize, or say minimize the average distance. But if they're for profit or not for profit. Like if they're for public goods versus private, wealth, they turn out to very different behavior. Okay, cheers.
I have a question about
All right.